In today's lesson, we are mastering the sum of infinite convergent geometric sequences. This topic is a cornerstone of the IB Diploma Mathematics Analysis and Approaches syllabus, appearing frequently in both Paper 1 and Paper 2. By the end of this session, you will be able to determine when a series converges and calculate its sum to infinity using the standard formula. This is essential for understanding limits and the behavior of long-term sequences, concepts that are vital for achieving those top marks in your examinations. An infinite geometric series is the sum of the terms of a geometric sequence that continues forever. We represent this as S infinity equals U1 plus U1 times R plus U1 times R squared and so on. Here, 1 is our first term, and R is the common ratio. But can we always find a single number that represents this infinite sum? The answer is no. A series only converges, meaning it approaches a specific finite limit, if the absolute value of the common ratio, R, is less than 1. In other words, R must be between -1 and 1. If R is outside this range, the terms get larger or alternate so wildly that the sum never settles. We call that a divergent series. When this condition is met, we use this elegant formula. The sum to infinity equals U1 divided by 1 minus R. It is important to understand why this formula works. We start with the formula for the sum of the first n terms of a geometric series. This is known as the partial sum. To find the sum to infinity, we look at what happens as n becomes infinitely large. We take the limit as n approaches infinity. Notice that the only part of the expression affected by n is r to the power of n. If the common ratio is a fraction between -1 and 1, raising it to a higher and higher power makes it smaller and smaller. Eventually, it vanishes to 0. When we substitute 0 for that limit, we are left with our sum to infinity formula. This is why the condition for convergence is so critical. Look at this visualization. As we add more terms, the sum gets closer and closer to the limit of 2, but it never actually crosses it. The horizontal asymptote represents our sum to infinity. Let us apply this to a typical problem. Consider the infinite geometric sequence, 18, 6, 2, and so on. We need to determine if the series converges, and if it does, find the sum. First, we identify our parameters. The first term, U sub 1, is 18. To find the common ratio R, we divide the second term by the first. R equals 6 over 18, which simplifies to 1/3. Next, we check the convergence condition. We need to see if the magnitude of R is less than 1. Since 1/3 is less than 1, the series converges. We are cleared to use our formula. Now, we substitute our values into the sum to infinity formula. This gives us 18 divided by 2/3. To solve this without a calculator, we multiply 18 by the reciprocal, 3 over 2. 18 divided by 2 is 9, and 9 times 3 is 27. The sum of this infinite sequence is exactly 27. Sometimes the IB examiners will give you the sum and ask you to work backwards to find a missing component, like the first term or the common ratio. In this problem, the sum of an infinite geometric series is 12.5, and the common ratio is 0.2. We need to find the first term, U1. We start by substituting our known values into the sum to infinity formula. This gives us 12.5 equals U1 divided by the quantity 1 minus 0.2. Simplifying the denominator, we have 12.5 equals U1 divided by 0.8. To isolate U1, we multiply both sides by 0.8. 12.5 times 0.8 equals 10. Therefore, the first term of this series is 10. This algebraic manipulation is a very common requirement in Paper 1, where you won't have a calculator to help you. Let's tackle an authentic IB-style question. This one combines multiple skills. The first term of an infinite geometric series is 3. The sum of the series is 8 times the second term. Find the common ratio R. To solve this, we translate the words into algebra. We know the first term is 3. The second term of any geometric sequence is U1 times R, which equals 3r. The problem states the sum to infinity is 8 times the second term. So S infinity equals 8 times 3r, which is 24r. Now, we use our sum to infinity formula. u1 over 1 minus r equals 24r. Substitute our value for u1. To solve for r, we multiply both sides by the denominator. Expanding the brackets, 3 equals 24r minus 24r squared. This is a quadratic equation. Let's move everything to one side and simplify by dividing by 3. Using the quadratic formula, where a is 8, b is -8, and c is 1. Simplifying the radical, root 32 is 4 root 2. So, r equals 2 plus or minus root 2, all over 4. We must check if these ratios allow for convergence. Since root 2 is about 1.41, both values result in an absolute value of r less than 1. Therefore, both are valid solutions. In IB examinations, small errors can cost you significant marks. Let's look at how to avoid them. The most common mistake is applying the sum to infinity formula when it isn't valid. Always check if the absolute value of r is less than 1. If r equals 1.5, for example, the series has no sum to infinity, and writing 1 down will lose you all accuracy marks. Students often stumble when the common ratio is negative. Remember that 1 minus r becomes 1 plus the positive value of r. If r is -1/3, the denominator is 4/3, not 2/3. Ensure you are using the actual first term of the series, not a general term or the common ratio itself, in the numerator of your formula. Read the question carefully. If the question asks for a specific number of terms, use the SN formula. Only use the sum to infinity formula when the question explicitly mentions an infinite series or the sum to infinity. When you are sitting your IB exam, keep these strategies in mind to maximize your score. Even if you are using a calculator for paper 2, always write down the sum to infinity formula and the values you are substituting. IB examiners award method marks for showing you know which tool to use. If you make a typing error on your calculator but have the substitution written down, you can still gain marks. If a question asks for the possible values of x that make a series converge, you are being tested on the modulus inequality. Absolute value of r is less than 1. This often leads to solving a double inequality or a quadratic inequality. In paper 1, questions are designed to simplify nicely. If you find yourself with an incredibly messy fraction, pause and recheck your division for the common ratio. Most paper 1 sums result in clean integers or simple fractions. Sometimes infinite series appear in geometric contexts, like a ball bouncing to a fraction of its previous height. In these cases, be careful with the first term. Sometimes the first bounce is not the same as the initial height from which the ball was dropped. Sketching a quick diagram can prevent this common trap. It is time to test your understanding. Please pause the video now and attempt these 3 questions. The easy question asks for the sum to infinity of the series starting with 10, 5, and 2.5. The medium question requires you to work backwards to find the first term when the sum is 40 and the ratio is 3/4. The hard question involves solving a system of equations. Take your time with these and then resume the video to check your solutions. Let's go through the solutions. For the easy question, our first term is 10 and the ratio is 5 divided by 10, which is 0.5. Since 0.5 is less than 1, we use the formula. 10 divided by 0.5 gives us a sum of 20. For the medium question, we substitute the known sum and ratio. 1 minus 3/4 is 1/4. To find u1, we multiply 40 by 1/4, giving us a first term of 10. For the hard question, we have 2 equations. Let's rewrite the sum to infinity as u1 equals 27 times the quantity 1 minus r. Now we substitute this into the first equation. 27 times 1 minus r plus 27 times 1 minus r times r equals 15. Divide everything by 3 to simplify, expanding the terms 9 minus 9r plus 9r minus 9r squared equals 5. The 9r terms cancel out, we are left with 9 minus 9r squared equals 5. Rearranging, 4 equals 9r squared. So r squared equals 4/9. Taking the square root gives us two possible values for the ratio, positive or negative 2/3. Both satisfy the convergence condition. To finish, let us recap the essential points from today's lesson on infinite geometric series. First, an infinite geometric series only has a finite sum if the absolute value of the common ratio is less than 1. Always verify this before calculating. Second, use the sum to infinity formula, where u1 is the first term and r is the common ratio. This formula is derived from the limit of the partial sums as n approaches infinity. Third, be prepared to rearrange the formula to find missing variables. IB questions often require you to solve for u1 or r, sometimes leading to quadratic equations or systems of equations. Finally, remember that in paper 1, you should provide exact answers, while in paper 2, you should give your answers to 3 significant figures, unless specified otherwise.